Hey, welcome to another episode of Math and Literals. Today, we are going to talk about a visualizable problem again. We will talk about a maximal problem. What is a maximal problem? Suppose you love to eat the pie that your mother makes. Now she has told you a very special thing about this. She said, you can eat as many pies as you want. But there is a restriction. You cannot fall ill with the pies. That means you can have no stomach ache, no tooth cavities, and no sign of weakness. Now this is quite a big problem for you. You cannot eat as many pies that you want, but you have to make the number of pies bigger and bigger in such a way that you won't fall ill. So this is a type of maximal problem. We have to maximize the number of pies here, and the restrictions are not letting us do the way we want to. So now let's dive into today's problem. We have to know about the following two things. A graph is a set of vertices and edges. Vertices you can think of points on a space, and edges are the connectors between the vertices. They may exist and they may not exist. Now you have to know about bipartite graph. From the word, look at bipartite. Bi means two, and partite you can think of parts. So basically, this bipartite graph has two parts with respect to the vertices. So over here, we have two sets of vertices, and any edge, look at their construction. They connect points from one set to the other set, and they do not connect points in the same set. So there can be no edges between these 2 points. So this kind of an edge is not allowed. Now what is the problem? Suppose in a space you have some vertices. Now you want to maximize the number of edges, but then the restriction is that no triangles are allowed. That means you can form no triangles. To solve this type of a problem, what we can do is we can try to find out a calculated guess and then prove that that guess cannot be crossed. Now we have learned about bipartite graphs a while ago. We asked the question, can bipartite graphs contain triangles? No, right? So this can be a good way to think of. Now, if a bipartite graph has n number of vertices, how many edges at most can it have? So of course it depends on how you divide it or how you partition it. But the question is how to partition it. How many edges can a bipartite graph with n vertices have? If you have divided the set of vertices in such a way that the first set contains x vertices and the second one contains n minus x vertices. So for every vertex of one set, if you connect it with all the other vertices of the other set, then you will have the highest number of edges. So it turns out to be x into n minus x. Now what is the condition that this product will be the highest given n? Now we get from differential equations usage that x has to be n by 2 if x were just a real number. But over here we are talking about edges. So x has to be a whole number. So the next best possible answer will be n minus 1 over 2 if n is odd. And the rest follows from this part. And if n is even, then of course x is equal to n by 2. Now let us try to implement that in this set. So over here we know that we have to divide it in two parts where there will be two vertices in one set, suppose these two, and the other two vertices will be in another set. So this happens to be that one. So now what will happen? We will get the bipartite graph like this. Now notice that it has exactly 4 many edges. If you draw any other edge to this, we end up getting a triangle in both the cases. Notice that we have considered all the edges possible over here. If we did the same thing with 5 vertices, then in one set we will have 2 vertices and in the other set we will have 3 vertices. So the graph will look like this. So till now we have learned that a bipartite graph contains no triangle and the number of edges in it has the value floor function of n square over 4. This is from the fact that if n square minus 1 over 4 is the number of edges where n is odd, then it is equal to n square by 4 floor function, and otherwise if n square by 4 is the number of edges where n is even, then it is of course equal to the floor function of itself. Now comes the question, is this number, floor function of n square by 2 for n, the biggest number such that these many edges can be drawn in a graph, but there will be no triangle, or can it be crossed? We will prove that the number is indeed floor function of n square by 4, and that comes via Mentel's theorem. So we need to prove that the number of edges in a triangle-free graph with n vertices is less than equal to the box function of, or the floor function of, n square over 4. Looks quite complicated, but it means that when n is even, we have to just show that the number is less than equal to n square over 4, and when it is odd, it is less than n square minus 1 over 4. But n square minus 1 over 4 is basically the biggest whole number divisible by 4 below n square by 4 when n is odd. So therefore we can write this, the whole sentence which we have written over here, as we need to prove that Tn, or the number that we want to find, is less or equal to n square over 4. So now our goal is to prove that the number of edges in a triangle-free graph with n vertices must be less than equal to n square over 4. Now we will prove it via induction, but there will be a difference. Generally, we try to prove in the final step of induction that if the statement is true for some natural number greater than equal to some specific number, then the statement is also true for n plus 1. But over here, notice that we have edges, and edges consists of 2 vertices. So if we want to discard one vertex, when we are dealing with edges, we have to actually discard 2 vertices simultaneously. So there will be a difference in the induction. Now notice that when we have one vertex or 2 vertex, we can go to the result directly just by looking at them. So therefore we know the result for 1 and 2. So therefore, if we now prove that if the statement is true for n, it implies that the statement is true for n plus 2, then we will be done, because 1 will imply 3 will imply 5, and so on, and 2 will imply 4, and 4 will imply 6, and so on. This will be our new goal. So having our base case done for 1 and 2, we now take the hypothesis that any triangle-free graph with n vertices follows the statement, and we have to prove for triangle-free graph with n plus 2 vertices. So we have to go down to n, and therefore we need to discard 2 vertices. Now, which vertices will we discard? We are dealing with edges, so we have to deal with the vertices which are adjacent. Now, if we remove such 2 vertices, then we will also remove an edge. Now, call that edge to be E. Now, this is the edge that we have discarded. And of course, the vertices adjacent to them. Now, without the 2 vertices, there will be a part in the graph. Let's call that the cloud. And now it has number of edges less or equal to n square over 4 because it is triangle free. Now the edge E has its vertices connected to some of the vertices in the cloud. Let us look at them. It might be like this. Some edges will be there. But now the number of edges going from the vertices of E to the cloud, that is to some vertex in the cloud, is less or equal to n because there are total n vertices in the cloud, and if some of the vertex in the cloud is connected or adjacent to both of the vertices in E, then there will be a triangle. So now we count the total number of edges. The cloud gives less or equal to n squared by 4 many edges. E itself was there, so we get one edge, and less or equal to n many edges from the vertices of E running into the cloud. So the total number of edges will be less or equal to sum of all of them, which will be n plus 2 whole square divided by 4. So we have reached our goal. Theorem n square over 4 is the number that we required. Now there is a question: does the bipartite graph that we have formed be the only choice for such a property to hold? You can think about that. That will be the discussion topic of the next video. I hope you enjoyed the video. Bye for now. Thank you.